Okay, is the screen visible?
Yes, sir.
Okay, just give me 1 minute. Yeah, the screen is still visible, right?
Yes, sir.
Okay, so let's start. And today, today we'll again continue with our discussion on CLT and LOLN. More on CLT, Central Limit Theorem, and Law of Large Numbers. So just to remind you, the reason for our enthusiasm with LOLN is that there is this intriguing situation that we may not know the average, but as the number of observations increases, the average tends toward the population average. So the sample size is, let's say, x1 to xn. As n tends to infinity, the sample mean tends to the population mean. So this is very intriguing. You may not know the population mean, but you move towards that. Okay, you move towards that as you increase the size of the observations. So as you observe more and more, the sample mean goes towards the population mean. Now, why should we only discuss with mean? So that bridge also we had built through the indicator function. So I may be interested in some parameter, and the parameter value approaches the true value as the number of observations increases. I may not know the true value, but it will as the number of observations increases, the parameter value will tend towards this. Now, parameter value and average value of observations, what is the link between them? The link is through what is called the indicator variable and the expected value of the indicator variable. So this is something you have to keep in mind, and we'll come back to this discussion. This subtle connection between some parameter value and all these results which involve the average value of some random variable. There is a bridge between the two. So today we'll do some proofs, and I'm afraid there will be lots of formula and lots of steps, but we'll go extremely slowly over this. Okay, and many of these things you know already. And these presentations are what are called academic entertainment, but entertainment with a method, okay, with a discipline. So we go over some proofs, in particular the proof of central limit theorem. And this is this presentation is more for showing you the beauty of mathematics, probability, statistics, along with the beauty of linguistics and language phenomena. So these proofs are indeed beautiful. So we'll go very, very slowly. If you get bored, please bear with me. If you do not understand, raise your hand or unmute yourself and speak. So statement and proof of CLT, the central limit theorem. Before that, we will first prove some lemma. We are very concerned with two quantities, the expectation and the variance. So the normal distribution you recall, has these two parameters, the mean value of the random variable and the variance of the values of the random variable. So expectation or the mean and the variance and or the standard deviation of the distribution are often of great interest to us. They're very basic. So mean is the measure of central tendency, and variance is the measure of dispersion. Now let's see this formulation. Let x1, x2, x3 up to xn be n independent random variables. We do not know what is the distribution of these random variables. One special case is when all these variables are independent random variables, but they're normally distributed with the same mean and standard deviation. That's a very special case. But let us not worry about that. Now, we have these n random variables and their distributions are unknown. What does distribution mean? Okay, many times we falter at understanding the meaning of distribution. Distribution means if it is a discrete distribution, then what is the probability that x, the random variable, will take a particular value a, or a value b or c or d, etc., and what is the probability of obtaining that value? For example, if the random variable is the outcome of throwing of dice, then the values would be 1, 2, 3 up to 6. So probability of x equal to 1, x equal to 2, etc. So now what we do is that given these n random variables, we take their sum. So Sn equal to x1 plus x2 plus x3 up to xn. Again, excuse me because there is a bit of sound outside. I'd like to close my window. This is better now. Okay, am I still audible? And this is visible, right? Screen is visible.
Yes.
Yeah. Okay. So Sn equal to x1 plus x2 up to xn. Then expectation of Sn is summation of expectation of x1, x2 up to xn. So expectation as an operator is distributive. Okay. So it distributes over the random variables. This proof is easy. We do not want to leave any proof undone today. But this particular proof, if necessary, we can do later. But we'll take up those proofs which are little more non-obvious. Okay, this is also non-obvious actually, but expectation distributes over summation. Now, another result is the variance of a sum of random variables is equal to the sum of variances. So expectation of the sum of random variables is sum of expectation. Variance of sum of random variables is sum of variances. So variance also distributes. Okay, so that proof we want. So let's go to the definition of variance. Variance is expectation of the square of the difference of the random variable from the mean. Okay, so I take values of the random variable and subtract the mean from these random variables, take their square and take their mean. So that is the standard way of obtaining the variance for special cases of discrete values of the random variable. But the definition of variance is that it is the expectation of x minus mean, where x is the random variable, the expectation of the square of the difference between the random variable and the mean. Okay, so the mathematical expression I think is clear to you. X minus mean, take the square and take the expectation. So Ex is the mean, so we write this as mu, so that our concentration is on a constant value. Expectation of a random variable is a constant value. So instead of writing Ex, we write mu to understand that expectation is a constant. So this point will be important. Now expectation of x minus mu square is x square minus 2x into mu plus mu square. This is the a minus b whole square formula. Now expectation distributes over the summation of quantities. So I can write this as expectation of x square minus expectation of 2 into x into mu plus expectation of mu square. This will be expectation of x square minus 2 into mu is a constant. So expectation of constant into random variable is constant into expectation of the random variable. So you can take out the constant. So this also can be proved from the definition of expectation. Okay. And then expectation of any constant is the constant itself, which again can be proved quite simply. So expectation of x square minus 2 mu square, because expectation of x is mu. So minus 2 mu square plus mu square. This is expectation of x square minus mu square, which is expectation of x square minus square of expectation. So in plain English, the definition of variance is quite elegant. That is, it is the difference between expectation of x square and the square of the expectation. Expectation of x square minus square of expectation. So see how this follows from the basic definition of variance, which is expectation of the square of the difference between the random variable and the mean. From there, by steps, we have come to the conclusion that the variance is expectation of x square minus square of the expectation. Square of the expectation is a constant, of course. So looking at this equivalence in plain English is instructive. Okay. Expectation of the square of the difference between random variable and the mean is equal to expectation of the square of the random variable minus the square of the expectation. Okay. So these steps I hope are clear to you. We are making use of two properties of expectation: the distributivity property, distribution over summation, and the property that expectation of constant into random variable is constant into expectation of random variable. So it is good for you to try to prove these theorems, mainly to flex and strengthen your muscles, mathematical muscles. So such exercises are good for exercising your mathematical abilities. Now we come to another observation that variance distributes over sum of random variables. So let's examine variance of x1 plus x2. We would like to prove that variance of x1 plus x2 is variance of x1 plus variance of x2. So always we go from first principles. Variance of x1 plus x2. If I look upon x1 plus x2 as a random variable y, then by definition variance of y is expectation of y square minus square of expectation of y. Expectation of y square minus square of expectation of y. So now y in this case is x1 plus x2. So e x1 plus x2 square minus expectation of x1 plus x2 whole, the square of this quantity. So I apply a plus b whole square. So x1 square plus 2x1 x2 plus x2 square minus e x1 plus x2, the square of this expectation. So expectation distributes over summation. So I can write this as e x1 plus e x2 square. So from the first term, I have got e x1 square plus 2 ex1 into ex2. What is the result I am using again? Expectation of constant into random variable is equal to constant into expectation of random variable. Another property we are using is expectation of product of random variables is equal to product of expectations. So expectation of product is product of expectations. Why so? This is because x1 and x2 are independent. Okay, so for random variables, two random variables which are independent of each other, the expectation of their products is equal to the product of their expectations. So this also can be proved using the properties of expectation and definition. Again, I encourage you to prove them so as to exercise your mathematical muscles. Plus expectation of x2 square. So this expectation is distributing over a plus b whole square formula minus. Now I apply a plus b whole square on this quantity ex1 plus ex2. So I have here ex1 square plus 2 ex1 into ex2 plus ex2 square. So now when I combine these quantities, I find that 2 ex1 ex2 cancels from the two expressions. And I am left with ex1 square minus ex1 whole square plus ex2 square minus ex2 whole square. So I have expectation of square minus square of expectation. Expectation of square minus square of expectation. So these are nothing but by definition variance of x1 plus variance of x2. Okay. So we are able to prove that variance of x1 plus x2 is variance of x1 plus variance of x2. So this is good. Now comes a little more intriguing observation. What happens to x1 minus x2? This part is the non-intuitive part. Expectation of x1 minus x2 is expectation of x1 minus expectation of x2. But variance of x1 minus x2 is not variance of x1 minus variance of x2. It is variance of x1 plus variance of x2. How to explain this intuitively? Okay, let us first see the maths. Variance of x1 minus x2 I can write as expectation of square minus square of expectation, as I know from the definition of variance. So this will be expectation of x1 minus x2 square minus expectation of x1 minus x2 whole square. So we are always using expectation, you see, and expectation right in the beginning we said is a very basic quantity for us, very useful and very frequently used quantity for us. And expectation is nothing but the population mean. If I take all values of x1 minus x2, then E will be the mean. Now I apply A minus B whole square formula. So expectation of x1 square minus 2x1 x2 plus x2 square minus expectation of x1 minus expectation of x2 whole square. So expectation retains the minus sign. Ex1 minus Ex2 whole square. So now I apply expectation over this whole sum and apply distributivity property. So expectation of x1 square minus 2 into Ex1 into Ex2, because x1 and x2 are independent random variables, plus Ex2 square. And here I apply again A minus B whole square formula. So minus Ex1 square minus 2Ex1 into Ex2 plus Ex2 square. So minus 2Ex1 into Ex2 cancels from the two expressions. Okay. And I'm left with expectation of square minus square of expectation for both x1 and x2. And I get variation var x1 plus var x2. So this part is non-intuitive. Okay. Variance of the difference is sum of variances, not difference of variances. And variance of sum is of course equal to sum of variances. Variance of difference is also sum of variances. How do you see this intuitively? Does it sound intuitive? How come the variance of difference is not difference of variances, but sum of variances? Anybody in the audience, can you explain this? Variance, you remember, is the distance from the mean, square of the distance from the mean.
Variance explains a sort of uncertainty about the observation. So if we are doing a linear combination, be it plus or minus, that uncertainty will only increase. So maybe that is the intuition.
Acha. So you are saying variance gives the uncertainty. I see. So relates to entropy somehow, and entropy only adds up, doesn't subtract. That is the kind of argument you're giving. Okay. Any other?
Sir, like when we subtract one random variable from other, random variable can have range from small value to high value. So when we're subtracting, the variance will not change, because while subtracting we can subtract the least possible value, so that the x1 minus x2 will have that high value, when even if we sum x1 plus x2 having a low value for x2, or low value, we will subtract having low value for x1 x2, that subtraction or summation will not change the output, so that variance will not change.
So variance of x1 minus x2 is the square of the distance from the mean of x1 minus x2. And mean of x1 minus x2 is mean of x1 minus mean of x2. So the means get subtracted and we possibly get a smaller mean. But you see, we are taking the square of the distance. Okay, square of the distance has the property of not cancelling each other. The square quantities only add up. Okay, which is why, for example, you take total sum square distance as a popular loss function. So the clue lies in the fact that the square of the distance from the mean only add up. Okay, they do not cancel each other. So that is at play. And also, both of your arguments, Nihar and Swarup, are also contributing to the understanding. But again, to flex and strengthen your intuition muscle, not mathematical muscle this time. Mathematical muscle is shown here through the step-by-step derivation. But to flex and strengthen your intuition muscle, you should, think about it and ponder over why variances add up even if the random variables are subtracted. The clue lies in the squaring of the distance. Okay. So let's.
I have one question here.
Yeah.
Are we assuming here that x1 and x2 are independent while calculating
X1 and
the
X2
weight?
are independent.
Yes, are we assuming, is there an assumption here while deriving
Yes,
this?
yes. Yeah, that assumption is there. Yeah. Okay. Now we come back to the statement of the central limit theorem. So let x1, x2 up to xn be n independent random variables, each with mean mu and variance sigma square. And also let Sn equal to x1, x2 up to xn. So that is another random variable, which is the summation of these random variables. Now comes the non-obvious statement, which is that Sn minus n mu divided by sigma root n. So sigma root n is nothing but the standard deviation. Standard deviation of Sn. So n into mu is the n times mean value, and sigma root n is the square root of the summation of variances. So let us apply whatever you have seen so far to this expression first. So what is the mean of Sn? The mean of Sn is, what is the expectation of Sn? This will be expectation of x1 plus expectation of x2 up to expectation of xn, all of which are mu. So expectation of Sn is n mu. And variance of Sn is variance of x1 plus variance of x2 up to variance of xn, which means n sigma square. So the variance of Sn is n sigma square, and this will be therefore Sn. So the standard deviation of Sn will be therefore root of n sigma square, which is sigma into root n. Now what I do is that I subtract n mu from Sn, because n mu is the expectation of Sn or the mean of Sn, and I divide it by the standard deviation of Sn. So I standardize the random variable. I subtract the mean. I divide it by the standard deviation. So far, there is no surprise. Now comes the punchline, that this Sn minus n mu by sigma root n is a normal distribution. Okay, so that is the theorem. Okay, so x1, x2 up to xn can be any random variables with any distribution, except that all of them have same mu and same sigma square. But Sn, their summation, will be a normal distribution with mean n mu and variance n sigma square. Okay, that part is the central limit theorem. And then, of course, if you subtract the mean, n mu, divided it by standard deviation, then you have what is called the standard normal distribution, where the mean is 0 and the standard deviation is 1. Okay. So is it clear to the class that the central limit theorem is saying that the summation is normal for sufficiently large n, of course. This will come in the proof. So if I take sufficiently large n, then whatever with the distribution of x1 to xn, only restriction is they must have the same mean and same sigma. What is a practical situation where this will happen? So let's take some random variables, maybe height and weight of a population. It is unlikely that their mean and standard deviation will be same. No. Let us take the income and the age distribution. Again, I don't see a situation where the mean and standard deviation are same. So mean and standard deviation being same, what does it mean? Isn't it a very artificial situation? No, if you convert all the random variables into standard, I mean, in the standard form, subtract the mean divided by standard deviation, then all of them will have mean 0 and standard deviation 1. So if you standardize the random variables, you come into the situation of same mean and same variance. But you might again object that this is also artificial. Okay, you are subtracting mean dividing by standard deviation. But I'm not very comfortable. Fine. So it is not very easy to find situations where the standard deviation and mean are same for each of these n random variables. No, it's not easy. Okay, but you can standardize them. Achha. So that is one part. The other non-trivial part is the fact that their summation is normal. Okay, with mean n mu and variance n sigma square. Which is the theorem part, the non-trivial part, the celebrated central limit theorem part, known for 2 centuries and used extensively again and again. Which is that part, which is the intriguing part? The fact that this is normal. Okay, there's a normal distribution. That is the non-trivial part, and it needs a proof. We'll proceed towards that. Another mathematical adjustment, which is also interesting, is this. I take Sn star, which is equal to Sn minus n mu sigma root n. I divide it by n. So then I have Sn minus n minus mu by sigma root n by n. So sigma by root n. And I have Sn minus n to be x bar, which is the population, which sample mean minus mu. So this is an alternative statement of central limit theorem, that x1, x2, x3 up to xn be n independent random variables forming a sample from a population with mean mu and variance sigma square. Then the sample mean is normally distributed with mean mu and variance sigma square by n, or standard deviation sigma by root n. Now you see the statement has changed. Though it is equivalent, it seems to be having a totally different flavor. So now we are saying that x1, x2, x3 up to xn be n independent random variables forming a sample from a population with mean mu and variance sigma square. So this statement is more intuitive. So I take a sample of maybe 25,000 people from the 1.5 crore population of Mumbai. I take this sample, and there is now a population mean, definite population mean, and definite population variance sigma square. So now I get a different statement of central limit theorem. The sample mean is normally distributed with mean mu and variance sigma square by n. I take different samples of 25,000 people. Okay, many different samples. Every time I'll have a different mean. Okay, and different standard deviation or variance. I observe the distribution of the mean. Okay, the sample has a mean of its own. The non-trivial part now is that this mean itself is normally distributed. That's non-trivial, right? That I don't think you had expected. The population distribution is not known. I don't know. I only know that the population has distribution as mean mu and variance sigma square. But lo and behold, the sample mean has normal distribution. Sample mean has normal distribution, and that means mean is mu, and its variance is sigma square by n. No, so these things are indeed very, very beautiful and very intriguing. Sample mean itself will be normally distributed. And its mean, the mean of that normal distribution is equal to population mean. Population mean has variance sigma square. Oh, that part is violated. The sample mean standard deviation is, variance is sigma square by n. Now, which statement of CLT you are comfortable with depends on your own, inclination and likings. The concept of a sample mean is intuitive. We understand this very well. So the concept of sample is understood well. So since the sample mean concept is intuitive and understandable, maybe the second statement of CLT you relate to better. And then you also sort of appreciate that if I go on changing the samples, taking different samples every time, and many such samples, okay, but each of, let's say, fixed size, then the mean itself has its own mean. The mean itself has its own variance. That mean is going to be population mean. That is non-trivial part. And the variance of the sample mean will be sigma square by mean, n. The variance of the population divided by n. That part is also non-trivial. But the most non-trivial and integral intriguing part is that this sample mean has a normal distribution. Not some unknown distribution, but it has a known distribution. That is normal distribution. That is not trivial. And the other statement is also nice, that I take the sum of these random variables, each of which have mean mu and variance sigma square. Then whatever be the distribution of x1 to xn, I don't know, but Sn must be normally distributed. Okay, so we are slow on this part, but I think I have sort of brought home to you this particular point, that the sum is normally distributed, the sample mean is normally distributed. Those you have to appreciate because they are not trivial and they require proof. Now let's move towards the proof, but before that, is there any question from the class?
Yes, sir. I have. When we consider the sample mean, so sample mean, and when we say it's a normal distribution, that time we consider this set of different samples, right? So set 1 will contain n samples, set 2 contain n, and the m number of sample set, and then we can say. So is this interpretation correct?
Yes.
Okay.
Yes. You go on observing the mean. and the mean itself will become a random variable now.
Yes. Right.
That random variable has mean mu, and variance as sigma square by n. Now, why is it? Why is the mean not disturbed, but the variance is disturbed? Is again something possibly trained to think this way, and maybe we did not find enough time in our college days, school days, or even BTech, MTech days, even PhD days. Maybe we did not find enough time to wonder about it. So at this point of time, I would like to digress a bit and allow me a little bit of liberty. Einstein apparently had said that understanding has three parts. So first of all, you look at the statement, you understand the meaning of each and every word of that definition. You put all these meanings of the individual words together, get the meaning of the whole statement. That understanding is called understanding of first part. Okay, so every action has equal and opposite reaction, and action and reaction act on two different bodies. So I understand the meaning of every. I understand the meaning of action, reaction, all those things. I understand that there is a main clause and there is a the two sentences are compound sentences. They have been put together. I understand syntax, semantics of each word, and semantics of the whole statement. That is understanding of the first part. Then comes if I am able to apply this knowledge. So I am faced with a situation. Suppose I tie a rope around a pillar. Okay. The pillar is firmly fixed on the ground, and I begin to pull that rope. What happens? I begin to go towards the pillar. The pillar doesn't move. I begin to go towards the pillar. Why? I am pulling the pillar. Why am I going to the pillar, near the pillar? Am I audible? Everybody is able to hear me?
Yes, sir.
Yeah. Okay.
Yes.
So I am pulling the pillar. How come I am going towards the pillar? Pillar is not coming to me. Why? Now I am applying Newton's third law. I am pulling the pillar. Pillar is also pulling me. Okay. And therefore I am going towards the pillar. This is application of the law. Believe me, some people will not be able to explain it this way. Okay. People, let's say, for example, people who have not gone through physics. Ask them, आप खींच रहे हो पिलर को, आप कैसे जा रहे हो पिलर की तरफ? How? They will not be able to explain because they have not seen this law. Now you are able to apply and explain. So this is understanding in the second part. Much more difficult is what caused the lawmaker to think this way and give the law. Why? Why did this law come? If you know that, then this is called the understanding of the third part. And if you have all these three parts, then you have understood this completely. This is what Einstein is reported to have said. So now, coming to the central limit theorem situation, I understand the central limit theorem statement. Summation follows normal distribution. I understand summation, I understand normal, I understand distribution. Put it together, I understand the state. First part. Second part is I'll apply it to solve some problem. Third part is why. Okay, why central limit theorem holds. And a part of that why question is this. Why the mean remains same, but the variance gets divided by n. Why? Okay. The other statement of the central limit theorem, the mean becomes summation of means. Okay. the variance becomes summation of variances. Okay, this is as per the properties of expectation and variance. All that is fine. There is no surprise here. It is simple mechanical application of variance and expectation. The non-trivial part is this, that this sum is normally distributed. So here the why questions is reduced to only one question. Why is this summation normally distributed? In the other equivalent statement, the why question is a little more intriguing, more difficult. Why is the variance divided by n? Okay, so let's think about this. It will only increase the power of our thinking and mathematical muscle. Okay. So now to prove the central limit theorem, so just remember what needs to be proved. We need to prove that Sn minus n mu divided by sigma into root n is a standard normal distribution. Okay, because Sn is normally distributed, therefore mean getting subtracted divided by the standard deviation should be a standard normal distribution. So this is what we are going to prove. So is it clear what is to be proved? Any question? What does the proof demand? The proof demands that Sn minus n mu by sigma root n is a standard normal distribution. That means it has mean 0, standard deviation 1, and it is a standard normal distribution. What does that mean? What does that mean? It means that Sn, the form of Sn necessarily has to be 1 by root 2 pi e to the power minus y square by 2. So y square is the value taken by Sn. Y is the value taken by Sn. So this will be the form of Sn, the summation of the random variables. Okay, its mean is 0. Summation minus n mu divided by n root sigma. Its mean is 0, standard deviation is 1. But the form is this. It is no other form. The form is 1 by root 2 pi e to the power minus y square by 2. No other form. So this is to be proved. And how does one prove it? One proves it from what is called the uniqueness theorem. Suppose x and y are random variables having moment generating functions mxt and myt respectively. Then x and y have the same probability distribution if and only if mxt is equal to myt. This is known as the uniqueness theorem. Now, am I discussing things which are elegant, intellectually very stimulating, but impractical? Am I discussing this such a thing? No. No. I am discussing things which are bread and butter of data science. Okay. Data science is founded on this. And the more and the stronger your grip on theory, better will you be at the practicals. Stronger your grip on theory, better you will be in the practicals. 100% guarantee. Okay. So, understanding uniqueness theorem, understanding moment generating function, understanding how to prove something is going to be beneficial in data science and therefore in AI, because AI is so data dependent these days. So that is the motivation for our theoretical work, mathematical thinking, intuition building, and so on. All that is needed because of this. Okay. So uniqueness theorem, once again, if x and y are random variables, then they are of same probability distribution if their moment generating functions are identical. So this takes the ball into another court now. we have to understand what is moment generating function. So let's go slowly. No hurry. Should not hurry on these things. So another 5 minutes or so, we'll continue these discussions in the next lecture. Let's understand MGF, moment generating function. So suppose X is a random variable, then the moment generating function of X is expressed by means of another parameter called T. So moment generating function of X is equal to expectation of e to the power Tx. So sometimes we say that, mathematicians' mind work in mysterious ways. Mathematicians' minds work in mysterious ways. So why would somebody think of taking X, multiply it by T, raise it to the power E, and take an expectation? Why would somebody do all this? Just repeating this. Take the random variable, multiply it by T, raise it to the power E, and take the expectation. Why? So the mind of such a person is working in a mysterious way, in an intriguing way. This person is seeing some truth which ordinary people are not seeing. Isn't it? Am I still audible to everybody?
Yes, sir.
Yeah. So this is an example of mind working at a level different from the ordinary. So do not look upon mathematical formula as lifeless symbols and expressions. They have a history behind them and they have motivation behind them. So I would like to take the expectation of e to the power tx. I'm not operating with x anymore, operating with e to the power tx and also its expectation. So see the importance of expectation, how many times it comes and how many situations we have to make use of expectation. So x is a random variable and its probability distribution function is given as fxj. Fxj is probability of x taking the value xj. So therefore, the moment generating function of x will be equal to mxt, which is equal to j equal to 1 to n e to the power txj fxj. So apply basic definition of expectation, which is you have to take all the values of this function of this quantity and take its probability distribution also. So expectation of e to the power tx is different values of e to the power tx and the probability of those values. Now here comes a little bit of subtlety, and do not take these things for granted when you are doing mathematical thinking. So
Here there will be one miss.
yeah, hello.
Hello, am I audible?
Yeah.
So for discrete distribution, if you say fx the way it is written equal to px equal to xj, that will be mistake for discrete, no?
Yeah. So what is the question?
So this fx for discrete distribution, that the definition, the way it is defined in the first line, x is random variable, fx is equal to p of x equal to xj, that is wrong for discrete.
Is it so? Oh,
sorry, that is wrong for continuous. What I have.
Continuous. Acha. So
we need to write another line.
what is missing there?
It should be a range. It should not be equal to xj.
No, range is minus infinity to plus infinity.
No, the definition of fx.
So fxj is fine, but fx is the probability density function.
Yes, that's
Yeah.
not just probability.
So that phrase has to be added. That's correct. Yes. So fx is probability density function for continuous distribution, and fx is probability mass function for discrete distribution. Isn't it? That's okay, Nihar?
Yeah.
Yeah. Density function for continuous, mass function for discrete. Okay. So mxt is equal to j equal to 1 to n e to the power txj fxj. Now you see the expectation of e to the power tx is equal to summation of values of e to the power tx and probability of those values. Now probability of e to the power tx is same as probability of x actually. So that part has to be kept in mind. Because E, T, these are constant symbols. So probability of e to the power tx is completely governed by the probability of x itself. So, so we come to this expression, and I'll just do 2 more slides and then we'll stop. This is the significance of MGF. The nth derivative of the MGF at t equal to 0 gives the nth moment of the distribution of the random variable. Thus, the first derivative at t equal to 0 gives the mean of the distribution. Second derivative at t equal to 0 minus the first derivative at t equal to 0 gives the variance. The third derivative at t equal to 0 along with the lower derivatives combined with proper operators at t equal to 0 gives the skewness. That is how symmetric is the distribution about the mean. Fourth derivative at t equal to 0 can lead to the kurtosis. That is how heavily the tails of a distribution differ from the tails of a normal distribution. Okay, kurtosis, skewness, mean, variance. Up to fourth moment, we have physical significance of the moments of these quantities. Okay, later it becomes simply mathematical quantities, not much real life correspondence. So mean is understandable, variance is understandable, skewness, kurtosis are also understandable. Now, proof regarding these nth derivatives. So I take the first derivative of the moment generating function. It will be d dt of e expectation of e tx. Now comes another thing, that expectation also is exchangeable with a derivative operator in with some restrictions. Okay, with some restrictions. So what those restrictions are, let us not worry about now. We just appeal to the definition of expectation of ETX. Expectation of ETX is ETX summation of ETX and probability mass function. I'm operating in the discrete domain. So then you can show, we'll spend time on this later, that E d dt of ETX is equal to x into ETX. This is simple derivative. And this is equal to EX when t is put as 0. So the derivative of the moment generating function at t equal to 0 gives me the expectation or the mean. Let's come to the second derivative. It is d dt of the first derivative. D dt of first derivative is expectation of x dx. The derivative can move inside. So expectation of d dt of x dx. So x square etx. Now t equal to 0, this will be ex square. And we know that ex square minus ex whole square. Okay, expectation of square minus square of expectation will give me the variance. So this I can see is the case. Second derivative of the moment generating function at equal to 0 minus first derivative at equal to 0 is the variance, and so on. Okay, so this is the
first derivative square in the subtraction term.
What is that?
In the subtraction term, it should be square of first derivative.
Square of first derivative. Yes, square of first derivative. That is true. Yes, square of the first derivative. So square of the moment generating functions differentiation. Yeah, that's true. So what does it buy us? What it buys us is that we'll show that the moment generating function of Sn, okay, the summation, is identical to the moment generating function of the standard normal distribution. The moment generating function of standard normal distribution is e to the power t square by 2. We'll show that the moment generating function of Sn star is also e to the power t square by 2. as n becomes larger and larger, which is why we insist that n process a threshold. That threshold is typically 30. Okay, now the proof will completely show you why the summation follows normal distribution and also why n should be large. We'll continue this proof in the next class. We are going slowly, but for a reason. Okay, so that's fine. So this was some mathematical work, and I feel and I hope it is still entertaining. I'm sure it is. So we'll continue this discussion. Okay, so the class is over. We'll meet 2 weeks later with these discussions. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.